Good afternoon, everyone. Thank you for joining us this afternoon. This is the F2 session, Regulatory Implications on Modeling. Stantec is our sponsor, and I would like to extend our thank to them for sponsoring this session. Our first presentation is called Carson Creek Flood Risk Reduction Project, Consequences of Redirecting a Creek. And our presenters are Sunit from HDR, Glenn Taffender from City of Austin Watershed Protection Department, and Sarah Davis from HDR. So with that, Sunit, take it away.
Thanks for being here for our presentation on Carson Creek Flood Risk Reduction Project, Consequences of Redirecting a Creek. And this is an exciting project that we worked on with City of Austin Watershed Protection Department. And for this presentation, we are going to tag team. So 3 of us will present. So just to give a brief introduction, my name is Sunit Dev, and I'm a water resources project manager with HDR. And I'm working with HDR for over 15 years now. And my project experience include flood studies, H&H 1D, 2D modeling, dam assessments, and dam breach analysis. And next one, we have Sarah.
Hi, I'm Sarah Davis. I'm a 3-year water resources EIT at HDR, and I'm also in the same group as Sunit in the dams, levees, and civil works group.
I'm Glenn Taffender with the City of Austin, been with the City of Austin for over 20 years, and most of my work is in stormwater management capital improvement projects. In this presentation, I'm going to provide an overview of the study area. Then Sunit will describe the background and problem areas, followed by the causes of flooding and challenges. Next, Sarah will discuss the risk reduction alternatives using HEC-RAS 2D. Sarah and I will finish with key findings and next steps. Let's get familiar with the study area. The project is located in the southeast part of Austin, Texas, near Austin Bergstrom International Airport. Austin is subject to flash flooding and is part of what has been called Flash Flood Alley. The Carson Creek watershed is one of more than 50 watersheds in Austin and has a drainage area of 6 square miles. The study area is a little less than half the watershed area at approximately 2.5 square miles and includes the main stem of Carson Creek, the Montopolis tributary, Tributary 2, Tributary 3, and Tributary 4 of Carson Creek. Carson Creek flows into the Colorado River. An interesting point of trivia is that during the cartography process for the rivers in Texas, the river names for the Brazos and the Colorado were switched. The project goals are to reduce the risk of flooding in the area and have a plan to account for the loss of flood storage volume when the quarries are filled. Now Sunit will describe the project background.
Okay, thank you, Glenn. So we will go through background and the problem areas for this watershed. So as Glenn mentioned, this watershed is on the southeast side of Austin, near airport, and the land use for the watershed is fairly urbanized. And just to give you a little orientation, the Carson Creek flows here on the south side, then crosses this Highway 183, and then travels further down and then joins Colorado River on the right side. Then it has a couple of tributaries. One major tributary is Montopolis tributary, which start on the north side of the main Carson Creek stem and then joins here. There are a couple of small tributaries, Tributary 2 and 3, and then another little bigger tributary called Tributary 4. And you will see later in the presentation, this main Carson Creek and then alignment of this Montopolis trib and trib 4 are really interesting, and we'll go over that in the presentation. So again, in the along main Carson Creek stem, most of the areas are commercial or industrial developed. but along the tributaries, most of the areas are residential. And on the south part of the watershed, there is Austin International Airport. And interestingly, there are few active or abandoned quarries in this area. And then again, this on this right side figure, which is rotated slightly, again to orient you, the Carson Creek comes here on the south side, and then Montapolis Strip comes from this left side and then joins Carson Creek. And you can see here highlighted red are 5 quarries, and those are area-wise, those are over 1/4 of the watershed. And importance of those quarries are they act as a sink and provide a lot of flood storage for this area, especially when Montapolis Strip and Trip 4 gets overtopped. All the water goes into these quarries and gets stored in those quarries. Then just wanted to show you how this watershed and particularly this project area have problems. So on the right side figure, you can see most of the area, the shaded blue, that is the effective floodplain, and all the areas are, especially when we are divided this into 3 different problem areas, where area 1 is on the north side. There is Thompson Lane here, and along the Thompson Lane there are businesses as well as single-family homes and mobile homes. Around 18 structures get flooded or within the FEMA floodplain. In the middle area, which is called as Bastrop Highway or Patan and Jet Lane, there about 10 structures get flooded, and for area C, which is on the southeast side, which is called as Dalton Lane. So in that area, there are a few residential structures, few commercial businesses, and then this Dalton Lane that runs here, there are a couple of crossings which crosses Carson Creek and the tributary 4. Both of those crossings get overtopped frequently and flood the area. So these are main problem areas that we are focusing our study on. Then just when we started studying this area, we wanted to go and check what causes these flooding, and we found some interesting things. So the first cause for flooding is disconnection of Montapolis Strip. You saw in our presentation title what's called as redirecting a creek. So you can see on the right side, we have 2 photographs. One is, both are USGS topo maps. The top one is from 1955, and then bottom one is 2019. They are topo maps for the same area. And you can see on the top photo, the Carson Creek runs through here, and then Montapolis Strip, it goes through here, but it doesn't join Carson Creek right here, but it keeps going on and then continues here. And if you remember, or if you see on the bottom picture, that's where we are calling it as tributary 4. And then Montapolis Strip comes here and it just disappears. There is no channel that carries this flow. So basically what happened is from 1955 to current day, there is a lot of development in this area, which just removed that main channel for Montapolis Strip, and it got just connected to Carson Creek, and the remnants of the Montapolis Strip is now called as tributary 4. And what it does is it sends all this water from Montapolis Strip overland and floods this whole area. The second cause for flooding is development within the floodplain, and I'm going to give you a couple of examples. So this area is where tributary 4 comes near Dalton Lane, and this is area where there was a quarry or big open area, but that was filled in by the owner. And if you just compare along this line, along the edge of that property, you can see the red one shows the 2007 LiDAR, where the blue one is 2017. So there is about almost up to 4 feet of fill along that area. And the problem with that is water from this north west side used to come here and get into this area. But now, because this land is all filled, you can see in this right picture, now the water cannot come in and gets into this area. So it just gets flooded, it backwaters into the properties upstream and floods this Dalton Lane. So this is just one of the example for land development. Another example is again near tributary 4. This is tributary 4, that's Dalton Lane. And you can see remnants of old natural channel on the downstream side and then wider upstream channel. But in the middle, you can see that land is developed and the bigger channel is now become really small ditch. And also there are few driveway culverts which constrict all the conveyance or the flow, and this area gets flooded. Another cause of flooding is undersized culverts in the area. So especially that's the Dalton Lane, and where Carson Creek crosses and the tributary 4 crosses, there are culverts which are undersized, and because of that the water gets ponded behind the roads and then eventually it overtops at both the locations. Another cause that we found during our analysis is this is the main Carson Creek, and now this is where Montopolis Strip joins Carson Creek, and there is that quarry Q2, and there is now a connection between the Carson Creek and quarry. So originally it was Carson Creek would directly, all the flow in the Carson Creek would go straight, but now because there is a connection, water flows and gets stored in the quarry, and then when this quarry gets overtopped, water flows on the other side. There's a big ridge here, so water flows on the other side. Instead of going all that water sending through here, now water flows on this side and then flooding all these houses and the businesses. So those are some of the causes, flooding causes that we found out during our analysis. And now Sarah is going to talk about all the challenges for looking into different alternatives.
All right, thank you, Sunit, for detailing out some of the challenges that, or some of the problems that come along with this watershed. I'm going to talk about the main challenge that Glenn introduced to us in the beginning, and it's these quarries that we find in the downstream portion of the watershed. Currently, there are 5, and only one of them is required to submit a closure plan with the city of Austin. All the others are grandfathered into the permitting system. And with that, the city normally regulates to prevent backfilling higher than the existing ground. But like Sunit said, they now act as sinks within the watershed. And if they go back to existing ground, we lose a lot of floodplain storage. With that being said, because there's so much uncertainty surrounding these quarries, whenever we were evaluating our solutions, we wanted to do the worst case scenario. And with that is all the quarries are filled, there's no storage within them, and then all the water comes back to Montopolis Tributary and Tributary 4. So you can kind of see a before and after right here with the terrain. So filled, all of these are filled to kind of, we don't really have any knowledge of the elevations prior to the quarry activity, so we filled them to the surrounding area height. Alternative base condition assumes that all of the overflow that was going from Montopolis Tributary to the quarries, or Tributary 4 to these quarries right here, is now kept within the watershed, which amounted to a volume of 310 acre-feet that now needs to be conveyed down these channels. And then in addition to that 310 acre-feet, on these quarries themselves, they generated about 450 acre-feet of volume of water that would be coming in this direction as well. So in total, our alternative base scenario, worst case condition, is 760 acre-feet of additional water compared to the existing conditions of the current watershed. And this is all using the existing 500 year, and the alternative base condition gives us about 33 structures that are inundated, which is 5 more than if the quarries weren't filled. just to model that scenario, you can see here as the watershed begins to fill up, you'll see the floodplain just gets massively large, and we like to joke that this is our Lake Carson. So just all inundated and not good for the residents of the area or business of the area. So we kind of wanted to come up with some solutions that help the residents and the business owners. Some other challenges that we face are just your general trying to construct anything within a floodplain that doesn't cause any adverse impacts, whether they're water surface elevation or just general erosion within the stream banks. And then there's obviously environmental and permitting constraints with reconstructing any kind of channel. Now I'm going to go into kind of the alternatives that we evaluated. And originally this model was a 1D model, but as you saw with our Lake Carson, a 1D model just doesn't really have the capabilities to capture all of that overflow back and forth between the two different stream channels. There were several different things that we looked at in this watershed. This picture is kind of a montage of all those different things. Overall, we had about 10 solutions, and only 2 of them were overall watershed, and all the others were kind of piecemeal that we wanted to see the specific effects for that area. The first one that I'm going to talk about is problem area A up here. In previous studies, they had hypothesized that this area was having like some local drainage issues, the ditches weren't big enough, this channel wasn't big enough, the driveway culverts were adding to the flooding. And while that is true, during our 2D study, we're able to show that there was a ton of water just overflowing out of Montopulous tributary this way. So we knew that in addition to improvements here, we had to do something in this area to be able to help all of the 18 people that were being inundated in that area. For problem area B, there is some in the terrain. You can kind of see that there's some local flood issues, but as far as creek flood issues, a lot of that is helped by the upstream detention here, and then there's some channel improvements. We did look into this large regional detention pond about right here, but with the amount of water that's coming in there and just how flat the watershed is, the volume that you would need to contain was over 1,000 acre-feet, which is just unfeasible for this area or any area. The last area down here, Dalton Lane, it overtopped significantly during the 100-year event. And right now that limits access to a watershed protection field office, which is very important during 100-year events or any sort of high rainfall events. So part of the solution down here was increasing the capacity of these 2 roadway crossings here. And overall, those are all structural solutions, but then we also looked at non-structural alternative in which we bought or proposed a buyout of any inundated structure. As far as the recommended alternative goes, it's kind of a combination of everything that we looked at that we thought felt best. Within, we have a significant channel improvements that go through both of these. We did look at reconnecting Montopulous tributary and kind of putting all the flow through Carson, but the channel gets so large that down here it's too big and you start impacting structures in this area that weren't even inundated in the first place. So we knew that we had to reconnect Montopulous tributary to tributary 4. Within that, the only real detention needed within the watershed is this overflow detention up here. Without that, your channel just becomes too large and too unfeasible. You see some other detention here that accounts for the 2-year flows. We don't want to increase our 2-year flows as those are more erosive, and we want to have a stable natural channel that we design. Move on. I'll show you a quick video of what happens whenever we implement these channel improvements. So not all flood water is contained within the channels, but that's okay. That's not our goal. Our goal is to reduce inundation or flood risk reduction for structures. And this solution ended up costing about I think we costed about $65 million. There could be a little bit more optimization and some phasing as far as individual approaches. Overall, it removes about 24 structures from the floodplain and then brings those 2 crossings of the creek into compliance, and also removes 172 acres out of the floodplain. A comparable solution to this would be the structural buyout, which we costed to be significantly less at about $38 million. It does remove 32 structures, but you have to consider that that doesn't account for social impacts to the residents or businesses, which is historically an economically disadvantaged community. So overall, key findings, I kind of mentioned some of these before. As far as a structural solution, you would have to reconnect Montopulous tributary to tributary 4 to get that realignment in a pre-development state. Montopulous tributary is responsible for a significant amount of the flooding near Problem Area A or Thompson Lane. So local improvements aren't going to help you as much as you would think. Channel improvements are absolutely necessary, and regional detention is unrealistic. For all of these, or most of these improvements, you're going to need some sort of nationwide permit 27 or an individual permit from the United States Army Corps. And to kind of reiterate what we have been going through, as far as Glenn said, these unregulated quarries are a major unknown and significant, have the potential to significantly worsen the flooding in this area. So it's important to work with property owners to help prevent any kind of worsening of the flooding. And in this case, the RAS 2D model was able to address creek flood issues, but like we said, it doesn't really account for local flood issues, specifically within Problem Area B. A comprehensive solution could be determined, and it could be funded or phased to account for incoming funding. So I'm going to let Glenn give us the next steps.
Okay, thank you, Sarah. And so the next steps, the City of Austin Watershed Protection Department is evaluating options in relationship to available funding. I am assuming that's the same for many communities out there, but this is a pretty complex issue, and my guess is that we will probably be taking this one step at a time, and with the ultimate goal of having a solution for those quarries being filled in. So thank you for your time listening to our presentation, and now we're going to go to questions in the live version.
Thank you very much for the very informative presentation. This concludes our first presentation, and with that, we're going to go through questions. We have 6 questions, or 5. The first one is from Al, and that is, how come the city was allowing developers to eliminate or size down the channels?
So these.
I'll answer that. Sorry, Sunit.
Yeah. Go ahead.
So in actuality, the area that was developed that way was developed when it was still in the county, so the city didn't have regulatory authority over that. Certainly in today's regulations, we would not allow that to occur. But you know, it's kind of one of those things where you're playing with the cards that were dealt you. So we are looking for ways to resolve that day forward.
Thank you. The second question comes from Peter. Was the modeling done using a hydrograph or a quasi-steady state flow assumption?
Yeah, go Sarah.
For this model, we use hydrographs at different inflows within the model. So for tributary 4 and Carson Creek, they were kind of at the inflow of the cross section, and then within the individual subbasins themselves, we put them where we had delineated near the tributary. So hydrographs.
Thank you. Next question comes from Jeff. Were the quarries acquired to provide for flood storage and to prevent future fill and development?
We have looked at that, but there has been no decision made. It would certainly be a great idea to acquire all that storage, but that's something that we're still continuing to evaluate. And so I'm not sure what we're going to do with that day forward. But right now, it looks like it would stay as land that could be developed based on future partnering with developers.
To add to that, within our proposed solution, the structural one, 2 of those smaller quarries that were within and next to Tributary 4 and Carson Creek, those were included, and that cost was included in the overall cost of the solution. But the 2 or the 3 larger quarries were not.
Thank you. Were you able to evaluate downstream impacts due to failed quarries and increased flow conveyance into the river?
I think this one is talking about outflow into the Colorado River. And for this, the scope of this project, we were just looking at impacts of water surface elevation within the watershed to make sure that we're not causing any adverse impacts to structures. As far as flow, it's very unlikely that the Colorado and the Carson Creek would peak at the same time, just because of the massive scale of the Colorado River watershed. So we weren't concerned with increasing the flows to the Colorado River. But in general, they were very close to pre-existing conditions anyways.
Okay. Did the city self-fund or did you use FEMA grants?
This project was completely funded by the city of Austin.
Okay. Rod's asking, with increased flow into Colorado with proposed changes, did it cause any problems in downstream? I think you kind of answered that, but if you want to answer it again.
Yeah, I kind of answered that. I guess the impacts, like I said, we looked at where water surface elevation, and then we did do an analysis of flows for the 2-year event because those are considered our more frequent that could cause erosion. So whenever we did have impacts for the 2-year event, that's when you see kind of detention for, we call it just 2-year detention.
Yeah, and just to add to that, these impacts are mainly just within the Carson Creek watershed, downstream areas, and not in the Colorado.
Okay. Thank you. Kevin's asking, did you evaluate erosion hazard related to flow breaching into the quarries?
Sunit, you want me to answer?
Yeah. So yeah, we didn't look into erosion related or velocities that goes into quarries, but we're mainly looking at the worst case scenario where we are filling in all the quarries and that flow was coming into the Carson Creek watershed. So if those quarries are available for storage, that will be beneficial than what we assumed.
Okay, thank you. Was there any evaluations to the results as a function of different cell sizes? And what was the final cell size in this small area?
The final cell size for this area was, in some areas in the creek bed, it may have been 25 by 25, but overall, I think it was 50 by 50 is what we went with. We didn't do any evaluations as far as varying the cell size, just what we thought was appropriate for the watershed and making sure to include break lines where we thought was necessary.
Yeah, and also we did use a validation for one of the observed storm event, and we had few observed high water marks. So when we did our model, we used that observed rainfall and observed high water marks to validate our model.
Thank you. And Judy's asking, would you get mitigation credit for restoring creek connection?
I'll let Glenn answer that one.
I wish I could, Sarah. I'm not really sure. I guess it might be possible, but we certainly didn't explore that as part of this. Our main thing is, to look at what it would take to restore the creek to where it was naturally, and then evaluate that in terms of how well it mitigates for our flood risk reduction in that portion of the watershed. But appreciate you offering that, because certainly we want to look into that.
Yeah, and again, this project was mainly like the high-level feasibility level study, where we are just looking at what kind of alternatives would work, and we need, as a next step, we need to look into the actual more detailed study, and we'll probably include those areas to consider in the next step.
Those conclude our. Thank you very much for the interesting presentation. We're going to move to our second presentation now. And it is called, the second presentation is called FEMA 2D Modeling with Floodways, Case Studies. And our presenters are Ferrin Affleck, Atkins, Namrata Batra, Atkins, and Somaya Sagarika, also from Atkins. Ferrin, please take it away.
Hi, my name is Ferrin Affleck, and I'm here with Namrata Batra and Somya Sagarika, and we wanted to share with you some work that we've done doing modeling, two-dimensional modeling with floodways for some projects with FEMA. So I'm gonna just kick this off with a couple of just high-level overview of 2D and 1D modeling and floodway concepts, and then I'll be turning it over to Somya and Namrata, who these are the engineers who really did the work and figured this stuff all out, and I just wanted them to share with you some of the things that they were able to accomplish. So first, just really quick, one-dimensional modeling is really the most kind of a very simple way of looking at how to model a stream. It's really designed to be for your typical river situation where all the water is generally flowing in one direction. It's pretty well confined. You know, water will rise and fall, but generally will keep flowing in the same direction. It's based on cross sections that reach across an entire stream width of the stream, and flow is moving perpendicular through those cross sections. Oftentimes, people don't account for storage when they're doing one-dimensional models. A two-dimensional model it's designed to capture the more complicated situations where you might have flow meandering around things or moving through an urban area, you know, splitting at different streams or going around houses, or in a natural environment you might have you know, lots of flow meanders or islands or split flows or things like that. So a two-dimensional model is built around having lots of tiny little elements that we often refer to as cells. You would kind of think of it as like a digital elevation model, except for the cells talk to each other and water can move in any direction from a cell. So you might have water moving in any direction or in multiple directions at the same time. It all just depends on how they're interacting with their neighbors. And then last, before we get into these case studies, the floodway concept, Floodway came about at a time when really two-dimensional modeling did not exist. It was everything was done with a one-dimensional type model even before HEC-RAS was around. And so the whole concept of floodway is built around a lot of one-dimensional assumptions. And because of that, it becomes very difficult to try to apply these standards on a two-dimensional when you have a two-dimensional model. Okay, so a big one, for example, is the one-dimensional model assumes a uniform cross elevation across the stream, where in a two-dimensional model you might have, you know, the right bank is got a higher water surface than the left bank, or if there's an obstruction, you'll see a kind of a surge of water getting around that obstruction. This really kind of complicates things when we're trying to build or develop a floodway that's defensible. So getting into case study number 1, this is a project in Mendocino County where we have 3 administrative floodways in the effective, and the county said, hey, we would like model-backed floodways here. And it's like, great, good idea. Looking at this image, you can see that the area is kind of a bowl where we have lots of tributaries, several tributaries draining into this bowl and then out of one outlet in the north. And then on the west side, it's urbanized, which kind of adds to some of the complexities. So at this point, I'm going to hand it over to Namrata and let her talk through how she solved this problem.
Thank you, Ferrin. So the modeling for Mendocino network involved developing a combined 1D 2D RAS model where the 1D channels were connected to the 2D area via a series of lateral weirs. The proposed 1D 2D floodway approach for this kind of network can be illustrated in 5 steps with a given flowchart. The first step is to determine floodway on the 1D portion, whether all the flow can stay within the channel below the surcharge. If not, second step is to compute what needs to overflow from the 1D portion to stay below the surcharge. Third step is to create steady-state models for the overflow paths and calibrate them to the 2D results. Step 3 and 4 require some iteration while comparing the 1D 2D results. Once a good match is done, floodway is determined in the overflow area. So the overall goal of the approach is to create a 1D model that approximates the 2D elevations for the natural profile and then create a floodway within that 1D model. So now I will go through the details of each step. In order to determine floodway on the 1D portion, the weirs were revised for each stream of the Mendocino network to force flow to stay within the channel. This was done by revising the weir coefficient to 0, which resulted in no flow to the 2D area and only 1D channel flow was allowed. As you can see in the image, we then evaluate the difference in water surface elevation with overflow versus no overflow condition. The surcharge greater than 1 is shown in red in this figure. Of the 4 steady streams with administrative floodways, only the Davis Creek has increases in water surface elevation within 1 foot for the administrative floodway limit of steady. For the other streams on the west, the surcharge limit is exceeded and we need to determine the overflows to achieve the allowable surcharge. Overflow paths are determined by breaking the lateral structure into multiple parts and checking the surcharge criteria for the channel and the overbanks. For example, here I have shown the Broadest Creek right overbank weir split into 3 parts with the overflow opening for BRR2, and the left overbank weir is split into 5 parts with overflow opening for BRL4. In order to determine the potential overflow paths, we used the depth velocity maps, which are generated in RASMapper from the 1D 2D analysis. And this process of determining the overflow paths while checking the channel and overbank surcharge criteria requires some iteration. And once we have successfully met the surcharge criteria, we can go to step 2. Step 2 is to compute what overflows from the 1D portion and determine the overflow paths. So here you can see the velocity vector plots for the overflow paths developing with time. Here we have the inflow hydrograph, which has a peak discharge around 230, and you can see how the flow is developing. So these are the overflows, and with time, at the peak time, the overflow paths coming from all different directions start merging together, going downstream. And the idea is to capture these overflow paths through the steady models. Step 3, we start creating the steady state models for these overflow paths. So for that, we used the velocity vector plots as a guidance to develop the natural profile for the 1D model. And we used the water surface elevation contours as a guideline for developing the cross sections. And you can note that the cross sections for the overflow model may not always be perpendicular to the floodplain, as the idea is to calibrate to the 2D results. Again, the 1D profile baseline and the cross sections were adjusted with several trials, comparing the results to the 2D overflow flooding. For the steady state flows, the results from 2D model lateral weir output hydrograph were used. There is another way we can use the 2D model results and do the profile flows, like they can be plotted along any cross section, and you can determine the flow change location and extract the flow from the 2D to the 1D model. Step 4. Once the equivalent steady state model is developed, the results are compared to the 2D model and also discussed with the community. So here you can see the floodplain from the steady state models for the area in between the Broaders and Mill Creek is shown in blue, and the floodplain on the background is from the 2D overflow model. So the floodplain compares quite well, and we further investigate and compare the water surface elevations from the steady state model as to the 2D overflow model. For most of the reaches, we see a tolerance of within 0.5 feet, and the results can be improved with more calibration efforts. They were high in the ponding area. Further, Manning's and ineffective areas and other parameters can be adjusted and calibrated to 1D results within the established tolerance limit for the 1D 2D modeled water surface elevation. So once we have a reasonable 1D equivalent floodplain, step 5, we determine floodway in the overflow area using the standard FEMA methods and also discuss with the community so that we can make any required changes. And that's how we develop the results, model-backed floodway results, and here you can see how they compare to the effective. Shown in red lines is our model-backed floodway as compared to the current administrative floodway, which was shown in yellow. So the new model-backed floodway compares very well to the administrative floodway on the upstream channels, and it does add new floodway on the overbank flow area. So this study provides significant improvements over the effective flood study with the new 1D 2D model and also a model-backed floodway approach. But it also has some limitations and challenges. There is no acceptable calibration tolerance for 1D to 2D results, and which differs from study to study. Though efforts were made to match the discharges and other parameters from the 2D overflow models, they may not represent the same unsteady flow condition. Another challenge for this kind of studies is the adding future updates and LOMARs, as it will require updating multiple models. And generating floodway data table still requires more FEMA guidance, especially for the overflow reaches. And we do look forward to more development, and thank you.
Great, thank you, Nimrata. The next one I wanted to cover is a study that we did for the Nisqually watershed, and that's the Nisqually River comes into the kind of the bottom of the Puget Sound, the south side of the Puget Sound. This is a little bit different situation where it's more of one big stream coming into an area that opens up and spreads out. It is kind of compact in that the terrain is sort of holding it all in, but there are some breakouts from the major stream, and then how the water spreads around is kind of interesting. So I have Somya Sagrika here, and she's going to talk about what she did to solve this one.
Thanks, Ferrin. Yeah, I'll walk through the steps that we took to develop the floodway on this 2D model. The first slide I have is going to give a little more overview of the methods, and then we'll go into details of each of the steps. So the first thing we did was we tried to use the Mendocino's procedure and try to build on the same concept of building a 1D model. So you can see the figure to the right, I have, we identified the major flow paths in the 2D model, and you can see the yellow arrows kind of show the major flow paths. The main channel is conveying most of the flow, and there was one big overflow or breakout flow downstream of the railroad, and then it goes back into the main channel, and some of it goes to another stream to the left, that's McAllister Creek, and then it goes north to the Puget Sound, and some of it also goes south where there is a huge storage area. The figure in the center is the water surface elevation map, and you can kind of see the 1 foot elevation contour. So that's how we also decided to come up with our cross sections for the 1D calibrated model. And after finalizing the 1D floodway, we tried to test it in the 2D model, and then we added some iterations of trying to see the surcharges and finalize the 2D model. So this slide talks about how we developed the 1D model. The figure to the right, you can kind of see the major flow paths. The arrows in green show where the water is moving, and I have the numbers associated. These are the flows in CFS, and like I said, you can see downstream of the railroad, there is a major breakout. It's 27,000 CFS that's coming out of this main channel, and then half of it makes back to the main channel downstream of another highway, and you can see 15,000 CFS goes from the main channel and makes it all the way to the west, which you can kind of see it's a pretty complicated area here. And the first thing after we identified was just to lay out our 1D model cross sections, and you can see from these number of overflow paths, the number of 1D models we thought we were gonna have to calibrate to the 2D model, right? But then you can see like the figure in the center, it's a lot of models. Usually we don't have a lot of budget, and every model is not necessary to be calibrated or might not like convey that much flow. So from there, we tried to filter and focus on which areas are more important or the community has concerns. And finally, since downstream of the main highway, I-5, where I'm showing downstream of it is heavily impacted by by tides, and this is not a major concern area for the communities. They're never going to encroach in these areas. There is a wildlife refuge in the center, so we decided not to chase those downstream flow paths. After that, then we looked at some of the other splits. You can see there is another split where the 800 CFS is going from the south, and it's a very insignificant flow that we don't have to chase it. So after like filtering all these models out, we decided to stick with the major river channel, and then the one overflow, that's the 15,000 CFS. And we decided to have those two and try to calibrate those two 1D models to our 2D water surface elevations. And once we had the calibrated model, we were within, overall, we were able to calibrate it through, there were some locations, of course, that you can't get close to half a foot of calibration, but overall, we were able to calibrate and match the water surface elevations pretty well. And we started encroaching on it and came up with our 1D floodway. And the next step, what we did was the 1D floodway that we came up with, we wanted to test that on our 2D model. So we took that polygon shape and tried to just use that in our 2D model by encroaching either. We did it with terrain. There are various steps or methods of doing it. You can use Mannings, or you can use the 2D flow connection lines to do that, but we went ahead and we modified our terrain and encroached everywhere else and wanted to see what kind of surcharges we are seeing with this 1D floodway that we derived. The first figure you can see to the left, that's shows the surcharges. Anything with yellow, orange, or red is a surcharge of more than a foot. And you can kind of see like all these spots right upstream of the highway on the left side. There is this major red area that's a high surcharge area, and also in some of the channel there was a big surcharge. So then we started from there, and then we did a lot of iterations of trying to modify the terrain and just moving the encroachments and testing them out. And I'll walk you through some of the major changes we did and how we finalized it. The second figure you see, the first big thing we added back was the storage area from the south. There is this area takes a lot of volume from the what we saw from the 2D model, and the first thing we did was add that back, and you can see how the surcharges kind of improved from that really dark red. You can see orange, so it's around 1.5 feet of surcharge, and then the next major improvement we did was all these pockets you're seeing upstream of this highway in the center. We try to play with it because there are some significant culverts that convey flow from the upstream part of the highway to the downstream. So we added that back in the floodway model, and you can see how the surcharges improved a lot. You can see the blue color is the negative surcharge, and we saw the velocities increased in this iteration. And when we were doing this, negative surcharges were still like questionable, and so we also went through some other iterations and we finalized our floodway. The new guidance that's coming up, I think, talks about including negative surcharges if there is increase in velocity. So these things can be easily addressed, but at the time we were doing, those were not clear. So we still went through a lot of other iterations and finalized our floodway. And when we finalized our 2D floodway, while doing these iterations, some of the considerations we took was existing developed area where the community concerns were. And you can see where my cursor is, where there is heavy development. Those are areas where historically they have been flooded. So it was okay to include those, and the community, since they have had so much historic flooding, they wanted conservative floodways. So this was acceptable for them. Some of the other things we looked was future development, and I mean, we didn't want to come up with a floodway with a bunch of holes in it. So trying to align where for future it's easy for them to develop areas. So we took that into consideration too while developing this floodway. The final slide I have, you can kind of see how our final 2D mud floodway compares to the depth velocities, which represent the high-risk areas, and our 2D floodway captures that very well. And I have the comparison to the 1D calibrated floodway. Our 2D floodway is definitely wider, but it was a good place to start. It was not completely something that we threw out, but it was a good place to start. So depending on how the project is or the model is, the complications of the model, sometimes it will fit very well. But for us, since we had this big storage area, that didn't work out. Another thing we also considered when we were doing the iterations, we also looked at the 10-year floodplain kind of when we were changing these encroachment areas, and that worked very well for this project. Depending on your model, it might work. 25-year might work. So checking some of the low frequencies helped us to save time trying to figure out the encroachment areas. And you can see the 10-year floodplain is aligned very closely with our floodway. I would correct that. The floodway is aligned very well with the 10-year floodplain here. And we had the FRR meeting recently, and the community really didn't have any concerns, and they were okay with how the floodway came up. And since they want conservative floodways, they were pretty okay with this. With this, I'll hand it over to Ferrin to talk about the third case study. Ferrin, back to you.
Okay, thank you, Soumya. So we just talked through a case where Namrata had worked through, lots of flows coming in and splitting out and dealing with that with 1D. And then Soumya talked about how she did similar, but then took it back into the 2D model to compare how it worked and then made some additional refinements. This next project that I'm going to talk about is on the Teton River in Idaho. There's a split, a north and a south fork of the Teton River. This project, I'll just touch on it really briefly. This project is not done yet. We started it actually before these other two, kind of at the cusp of this whole 2D movement. HECRAS 2D wasn't available at the time we started this project. And essentially what we found using different software was flows were going everywhere, as shown in this slide. And trying to comply with the standards for a surcharge on a floodway, no surcharges at all, we ended up with a very wide floodway shown in yellow here. Obviously, this was a concern for the community. And so I think really all I wanted to touch on here is the takeaway is we stopped, we slowed down, right? We with FEMA and the communities had a conversation, multiple conversations, and slowed this whole thing down and said, hey, wait, before we go slapping something together that's just way too conservative, let's talk about it, understand it, and see if we can come up with something that makes more sense. And so we're still working on it. We'll probably take some of these lessons learned from these other two projects and apply them to this one. But the takeaway is to just, these are non-standard situations, and it's okay to take time to talk them through with everybody rather than just bulldozing ahead. So I'm going to wrap it up. Really, just as kind of my closing slides here, two-dimensional modeling is becoming the norm. We should expect it. FEMA's working to catch the standards up with the industry. But in the meantime, we've got to be kind of creative in how we deal with the technology we have and the standards we have. And then lastly is just talk it out. Transparency and collaboration with stakeholders is super important. And that way you can come up with something that everybody feels is a reputable product. And with that, I thank you for your time and attention, and we'll answer some questions.
Well, thank you very much for the great presentation. We're going to go through the questions. So the first one is from Nick. Would it be possible to only use a 2D model for this study?
Okay, I think that was referring to the Mendocino study, if I understood right. First of all, I got to apologize. Namrata really knows this study better than I do, so I can't answer a lot of super detailed questions on the Mendocino study, but I can connect you to her if you'd like outside of this. As far as I understand, they started with the 2D model and found that they needed to come up with a floodway that worked, and using the 1D, a 1D calibrated to the 2D model was the most efficient way they could come up with to work that study out. So I guess the answer is no, sort of. So.
Thank you very much. Next question. Do you think the shift to flood risk 2.0 will help make this approach easier to administer?
Okay, and I'm not an expert on flood risk 2.0. I think I'll try not to get into that too much, but I think that's more about rating of insurance and not so much about floodway administration. So probably not.
Right.
So.
Moving on to next question. How did you deal with tidal flows during modeling?
Okay, was this on this must have been on Nisqually, right? Okay, Sonia,
yeah.
do you want to take that?
Sure. So the initial 2D model tied into the tidal or the coastal zone So we used the mean higher high water elevation as our tie-in for modeling purpose, but for mapping purpose, I think if you remember, there was a big highway, so we had to stop it there because the tidal elevations were higher than our model. So that did not impact the 2D portion much where we were trying to resolve it since the elevations were higher. But
The coastal elevation.
yes, the coastal elevations were higher than our 2D elevations.
Thank you. Debbie's asking, what is the motivation to determine a floodway in a 1D model when it's clear that the 1D does not accurately represent the flooding?
I think this is for the Nisqually project, right? So, I think the idea, maybe I'll let you take it more. I think the idea was to let the 1D model help us figure out where we wanted to go with it before we did lots of iterations in 2D. Soumya, is that right? Do you want to elaborate?
Yeah, if it's particular to the model, we did have a 1D in the channel. So in the first test runs, we were like, maybe it can take it all. So we tried to start with a 1D model, and the overflow was pretty wide enough. There were not a lot of back and forth splits, or we thought we could handle it, but clearly it was more complicated for a 1D model, having the storage area. Because some of the guidance is also not clear on this, when how to do, like 1D is usually more acceptable approach if you for floodway analysis and including encroachments in it too.
Thank you. Rachel's asking, did you consider using unsteady 1D instead of steady state, since it would be a bit less of a deviation from the 2D base model?
I think that question is for the Mendocino study. I believe the team was looking to, the Mendocino study came before the Nisqually study, right? So it was a little bit further back in time, but they were trying to come up with a floodway approach that best aligned with what a floodway is. And the floodway concept is all very much one-dimensional and steady state in theory. And so I think that's why they said, okay, we'll get a 1D steady state model that does the same thing as a 2D unsteady state model, and then make a floodway. I think that was the reasoning behind the decisions made.
Thank you. Paul's asking, how did you modify your 2D elements to match the 1D floodway encroachments?
I think that's for you, Soumya.
He's also asking whether the 1D model was calibrated.
We did a 2D floodways. I'm a little confused with the 1D. Could you repeat that question, maybe?
So the first question was, how did you modify your 2D elements to match the 1D floodway encroachments? Let's answer this one first.
Okay, yeah. So we used terrain. We just built a tool in ArcGIS so we could replicate the terrain. What I did was take the encroachments that I was seeing, elevations, and kind of just gave a flat terrain that we could encroach. But you could also use Manning's, especially in HECRAS 2D, you can use Manning's polygon and just give higher values and have the same results.
Okay, and he's also asking if the 1D model was calibrated.
Yes, the 1D model, the initial when we started on Nisqually project, we calibrated it to the 2D elevations. It definitely was very complex, especially the number of lateral weirs we had. We had convergence issues, so we kept it simple to just match the flows and the elevations. So we had to manually give flows to cross sections instead of trying to make the 1D model work and interact with both the splits. And I think overall we were within half a foot of the 2D elevations. And there were locations where we were more off, especially around structures, since the slope and how 2D, I mean, there are different modeling methods or calculation methods. So there were spots where we deviated, but overall we were able to match it by half a foot.
Thank you. Can you comment on the decision that a flow path was deemed hydraulically insignificant with close to 800 CFS? Bobby's asking that, and they had experienced similar issues in their modeling, and they struggled to confidently rule out a flow path.
Yeah, that's a good question. With our with the river, the total 100-year flow, or the 1% chance, was around 63,000. So compared to that amount of flow, 800 is not going to make a huge impact on the encroachment. So that's a good way to check. And we also looked at the, when we were doing a lot of iterations, we looked at the 10-year, or so you can check your some of the low frequency flows. If that 800 or that smaller flow path is not shown, you could encroach on it. Especially, I think that spot I was talking about upstream, it was coming from the upstream of the railroad. It was coming from the main channel. So upstream of the railroad was a 1D model, not a 2D model. In that 1D, we did not need that 800 or the separate flow path. We were able to encroach it. So that kind of helped us guide that, okay, we can still keep it in the channel.
Thank you. Did the 2D model use a rating curve or time series for the downstream discharge to account for tidal influence?
So
yeah, go for
I think that was answered before. The model used just the mean high or high water as just a flat line. So it didn't use unsteady boundary condition.
Were the results of the Mendocino project developed for a LOMAR or PMR? And if so, did it receive FEMA approval and replace the effective model?
Yeah, great question. Yes, it was for a PMR, and they vetted the method through the region before they finalized and used it. But the answer is yes, it was.
This concludes our questions. Thank you very much. And this basically concludes the second presentation. We can now move on to our third presentation, titled FEMA Approach on 2D Floodways, Improving Tools and Updating Guidance. Our presenters are Rick Sacbibit, Laura Algio, and Brian Coper. Rick, take it away.
Hi, welcome to our presentation today. We're going to give you some background and update on where FEMA is related to two-dimensional floodway modeling, along with our guidance and regulations, and where we're at and some changes that we're making. For the presentation today, we had a few people identified to present. We had Rick Sacbibit, who is with the Engineering Services branch. He's the branch chief. Myself is Laura Algio, also with Engineering Services at FEMA, and Brian Coper, who will be presenting. Rick is not going to be doing any of the presentation today, but he will be on for the Q&A immediately following this session. So some of the things that we're going to talk about, just sort of why we're doing these updates, what's going on, give you a little bit of a background on the integrated project team that was pulled together to start looking at the challenges around 2D modeling and the floodway component of those, go through some of the goals and some of the standards and guidance changes that we're talking about making this fall. And we'll give you a little bit of background on those guidance and standards and the timeline and next steps for that. So the 2D floodway modeling, obviously the 2D modeling has been around for many, many years. But in 2016, HEC RAS 5 was released, which made a free avenue for 2D modeling to be developed. Through that model update, there were 2D components. And so there seems to be a larger increase in the number of people actually doing and performing 2D modeling. Our floodway regulations are written into the Code of Federal Regulations back in the 70s, and they are very much focused on the one-dimensional concepts and approaches. those don't translate very well to the two-dimensional modeling and the way that it gets set up with gridding and other modeling components. So there's really, as more and more people have been doing the 2D modeling, we've identified the need to really take a look at our standards, take a look at our guidance, and see what is it that needs to be modified and changed to understand the differences in the modeling components, still meeting our Code of Federal Regulations, which is still in place, but trying to give some flexibility and leeway around the modeling components that are being done these days. So we pulled together an integrated project team. We really wanted to get feedback from the user community. These are not just things that we want one or two people to start to make decisions on. We want to try to get feedback from the user community as a whole. So we do have a few executive sponsors at the FEMA level. And then our membership is really broad, composing our production and technical services contractors, which are our contractors out there that contract directly with FEMA doing flood studies and updates. The Cooperating Technical Partners Program, which are state, local, regional organizations that do flood studies with FEMA, the FEMA regions themselves. There's also been a lot of input by Federal Highway Administration, who've been doing work in Colorado and working with their 2D consortium, as well as the Army Corps of Engineers, HEC in general, and our community engagement and risk communication contractors. So really trying to get a broad input from folks on the types of changes that might need to be made, how we can show this information, share this information, and have it be cohesive and also easily understood and usable and meeting our federal regulations. So we really define sort of some short-term and long-term goals through that IPT. Phase one in the short term is really trying to understand what are these allowable approaches to floodway. You know, we have 1D already. There could be 1D steady state, unsteady state. There could be mixed models. You know, what are these allowable approaches that we can take? We started looking at surcharge compliance. You know, it's currently based on the one-dimensional methodology of a 1 foot increase. That is in our Code of Federal Regulations. We have to maintain that. However, a lot of folks are utilizing depth times velocity and other risk components, and we want to be cognizant and recognize those risk components, but also we have to take it back to that regulation and make sure that it's meeting our regulations. We looking at our guidelines and standards to say where do we have flexibility within those guidelines and standards to account for some of these new components and some of these new methodologies through the two-dimensional world, but also making sure that we're taking it back to holding the line of our regulations, but taking this information in. And then also identifying what are some training needs that we have. You know, people are going to not really be able to understand the 2D modeling potentially as well as they can understand one-dimensional results anyway. Local communities, especially those communities that have less access to the internet and some of the tools that are available in that realm, may have more difficulty understanding this information. So really trying to understand what we need to do and how we need to present this information in a way that the user community can really understand it. Keeping in mind that the user community is not always the engineers and the folks that are developing the modeling. And then we also have phase two, which is our long term, where we're really looking at, do we need to look at changing our Code of Federal Regulations? That is a very long-term process, and it's one that if we never get started, we won't, right? So we are looking at what we might need to do, but also trying to understand, is the 1 foot rise appropriate or not? Should it be something different? Should there be something looking at depth and velocity and looking more at risk components as opposed to this 1D element of a foot of rise or less in communities that allow it? And really trying to understand what opportunities we have there. So this presentation, though, is going to focus mostly on the results and where we're at with the short-term results. Those are the things that we're trying to get incorporated for this upcoming guidance cycle so that we can start to allow communities that are already doing this work to better understand what their requirements are and what they need to do to develop their studies in accordance with FEMA guidance. So as part of this IPT, we broke into different groups. We identified a subset of standards that needed to be updated that talk about the floodway components and where models tie in. And we broke that into 3 groups and had breakouts by different volunteers throughout the IPT that went and looked at these different components to try to come up with some language to update. So group 1 looked at really where we have averaging and doing the floodway setup. Group 2 looked at those tie-ins and profiles and how those are connected in a 2D world. And then group 3 looked at outputs. So you can see the legend on the right-hand side of the slide. The gray indicates that through our review, we determined that there were no updates needed. In green, it means there were some minor changes that we made. Red is we actually rescinded the standard. And blue means that there were some significant changes that we made based on the conversations with the IPT from the input of all of the stakeholders. So some of the standards that are being updated, we'll start with group 1. I won't go over the ones in green and gray. Those are basic general updates. The 2 that I want to really focus on this group are 73 and 77, which talk about the equal conveyance reduction methodology for 77. We removed the language around equal conveyance, which is really tied to a methodology in HEC RISE. And while some people start their modeling for floodways based on a depth times velocity, which is great for risk, it doesn't always take into account the fact that the floodway is an artificial determination of an area, correct? So there's not actually that development there. And so we really want to make sure, though, that the language is clear about that equality between the communities. So we inserted language related to equitable distribution across the study area. So that really gets to being able to make sure that we're equitable across communities, but we're also taking into account the other risk components and things that we can do with 2D modeling. And 77 is the other major change from group 1, which really talks about coincident peaks. And it just talks about the fact that we should be requiring coincident frequency analysis, or using a documented historical observations if we're using backwater as a starting condition. Oops, sorry. For group 2, the main change was really for 128. The other ones really just do some minor clarifications or don't change. For 128, it talks about for floodplains being mapped in 2D, separate profiles and significant flow paths must be created. What we're doing is allowing through this change is for the capability of putting those BFE lines, which have historically been at the whole foot interval, to be placed at a 1/10 of a foot interval or up to a 1/10 of a foot as needed. That match the model. So those BFE lines would be exactly where the modeling information shows that elevation at, and being able to show that to a 1/10 of a foot. We also stated that, if you enter into situations where you have a really steep area or some concerns, you may still need a profile. You may not be able to put a 1/10 of a foot BFE lines into the map and still be able to see. So we also have a flood insurance study report insert terminology that's being used now. Typically that's been just your traditional profile. We're sort of making the language a little bit more generic to allow for some additional components. So some types of inserts that will be described more clearly in guidance may be a gridded, your gridded area with the base flood elevations for each grid, so that somebody could zoom in a pullout in the phys text and be able to see more granularity, or potentially doing those BFE lines at more granularity in a pullout. So taking a smaller section than you would have for the entire firm panel and being able to zoom into those areas that are a little bit more that need more detail and being able to pull the information there, or also potentially still just doing the flood insurance study profile. That is always an option if it's something that is doable for that modeled area. And then lastly, in group 3, we talk about the floodway, the major changes related to the floodway data table, and that's really just adding references around floodway evaluation lines. So as we're doing the floodway analysis, we're trying to identify something similar to the 1D world, where you're not looking at every single grid point, but you're taking an evaluation line across the floodplain that you would then do your floodway evaluations on. So there's language added to that, and then the required attributes fields are modified. The main thing will be to check in the flood insurance study report and technical reference, technical reference and guidance document, because that's where all of this is going to be detailed much more clearly as we go into the guidance sections. Next up, we have Brian talking about some of the examples and the next steps.
Yeah, as Laura mentioned, evaluation lines is one of the new features that we're thinking of for 2D models. And what you see here on the right side of the slide is an example of that there. And along with the complexity of 2D models and the capability with 2D models, it brings the added challenge of how do we show this on the map. So the capability increases the data that we have, but also displaying this from the 2D world onto the map, which is a lot of times we've been using it as from the 1D perspective. So this what you see here is a 1, 2, and 3 step process to do that calculation of evaluation line. The red and the green and the yellow there are the surcharges. So you'll see areas where you have the 0.6 surcharge, 0.3 down the center line of the channel, and then a little bit of a negative surcharge on the left side there of the figure. And so when you take that average, which is shown in the pink there across the top, you'll get an average similar to what you do for a cross section. And so that's in a nutshell what we're thinking of, and placing these evaluation lines at strategic locations, similar to how cross sections are placed in a 1D world. So that would be a way to in a sense replicate what we've already done in a 1D world into the 2D world, where floodplain managers, communities can use these lines and evaluate where the surcharges are. And that more will come in guidance. We've talked a lot about now the standards, so the details and how this will all be done is going to come into the guidance part of it. So we'll go to the next slide here. So this shows another image of a sort of a complex flooding area here on the right, and you have BFE lines that are shown, and what's coming up in red are half-foot elevations that we can show. So if a whole foot elevation of a BFE isn't enough, we can show decimal BFEs, and that's what you see coming up in red. And then the points A and B are maybe areas where you want to get more precise, and so even at those places you can get to the decimal BFE location perhaps for those areas that aren't maybe necessarily along a stream center line, along a profile baseline, and where you may not have an easy way to get a BFE other than looking at the map and having those additional points to reference. Slide. And now you heard a little bit about BFE insert or FIS insert for BFEs, and that's what you see on the left side of the screen. There is an example insert, which we're thinking of is a way it really combines the grid of a 2D model and the elevations at each of those nodes, along with the BFE lines, which you could use to better average elevations in between those lines. So it kind of gives you the best of both worlds, where you have a grid, you can average and get linear interpolation between those nodes, but then also the BFE lines aid the user there on the left side to maybe linear interpolate in between those BFE lines along with the grid, depending on the topography. And so BFE lines are really the tool that we've been using, and so we want to continue to use them because they really are the best way to show the BFE on the map, because of the flexibility in using the model, using the topography, using the conveyance to plot those BFEs on the map. So it's all those products together that's used in the modeling as a way to graphically display them on the map, and they hold a lot of power. And so when placing these BFE lines, we want to make sure that we're continuing to put them in the right spots, so that the map user can go to the map and trust if they do a linear interpolation that they're going to be able to get a precise BFE at that location. And so the right side of the screen shows perhaps additional profiles we could put in. So you normally a main centerline profile, but additional profiles can be added if needed, depending on the breakout flows, split flows, things like that. So if we need additional profile, we can put one in, but also that we don't want to clutter the map too much either. So it's a balance, and probably be a case-by-case situation on how many profile baselines to use, how many profiles to use versus BFE lines, because we also want the products to be usable. So usability is one of the keystone tenets that we're going to keep in mind, because ultimately we still do have maps. It's not everything's not digital where you can zoom in, to very granular locations. So we have to keep an effective regulatory map scale, but also have the digital capability of the NFHL is a way to use what we can. And guidance updates are coming. We've mentioned that, but the 2D topic, especially for floodways, it touches a lot of different guidance documents. So we've listed a few there on the screen, but it's really we want to make sure we're touching all the right guidance documents, because floodways and there's a lot that goes into it from the cartographic standpoint on how to show it on the map, how to calculate it from our modeling, and then how do we use the profiles and things that we have in the 1D world. How do we make sure that they carry over to 2D models? So there's a lot of different guidance documents that we're going to be touching, and we're going to make sure we're doing a holistic guidance cycle update so that we're not leaving anything out. And this is an annual cycle, so this year is just this year's update. There'll probably be updates future years as usual. So as we collect any best practices, we could always make future updates to the guidance cycle. Okay, next slide. And speaking of the guidance cycle, that's the schedule there for this year on the screen, or for this cycle. It's a 1-year period that you see from front to back of the schedule, and what's highlighted there are a couple places for input from the public review side. So every month we have an engineering and mapping COP. It's the first Thursday of the month, and this is a forum where we present those guidance changes, present the suggested changes to the engineering community. And so that's one way to get engaged. Other ways are through sending an email. That's what you see on the bottom of the screen there, fema.gs@riskmapcds.com. And you'll see this guidance cycle is not specific to 2D or not specific to floodways. It's the general guidance cycle. So if you're involved with other parts of our guidance or our standards updates, this will be the schedule that you'll follow. And it just shows some of the key areas there. So look out for that in the coming months. And so next steps, we touched a little bit about already. And so floodway alternatives, we're in the process of generating these is a way to build on our standard changes, what we've talked about already today. So in getting through those, the testing of these, then we'll really be able to build out the guidance some more to get to the details of how to do the things that we're needing to do. So it's a piecewise process, but it's coming up, and we're actively testing various alternatives across the country to make sure that from a geography standpoint that what works down in very, very flat areas of the country could also work in very steep areas of the country. So we have to look at it from a national perspective to make sure that we're getting a representation that would apply nationally. And so along with that comes the tools, and we are using an S at the end of the tools. So a lot of this may not just be a one tool, fixes everything, because it probably would take maybe a suite of tools depending on where you are and case by case across the country. So we're really wanting not to be prescriptive or narrow, saying that there's only one way to do it. We're thinking that depending on the geography, there may be various ways of calculating it, but just to make sure that they're staying within the standards, staying within our guidance, and then looking again at best practices or long-term updates, regulations we talked about a little bit already, but other ways that we can improve our guidance based on the best practices we see and the ways that this gets implemented. So we'll learn more as implementation unfolds, and then we'll continue to make updates to our guidance as needed. And for any questions, we'll take that now as a portion of the presentation. If you don't want to have questions or comments today, you see the email addresses for all of our presenters here on the screen, and you can feel free to email any of us.
Well, thank you very much for the very informative presentation. I want to bring everyone's attention to the resources tab right under the presentation area. If you look at it and if you click on it, it will take you to it. Basically, the handout for this presentation is there. And it's called Proposed Revisions to 2D Floodway Modeling Standards for FY20 GSSC cycle. So please check it out. Now we're going to go through the questions. First question for SID 128, was there any consideration given to moving on from profiles? Results from 2D models provide more complete and geographically locatable than simple profiles.
So thanks, EMAC. And I'm seeing a lot of questions related to products and things of the future. And this is a great question. What do we do with profiles? How do we start to look at some of the underlying information that 2D modeling can bring to the table, whether it be water surface elevation or something to that effect. So there's quite a bit of information that I think we can unlock down the road. We're looking at the future of flood risk data within our own program. We're seeing the expansion of 2D modeling being used throughout our program. There's also elements that we're trying to consider as we start to look at our products. Maybe the firm looks different, maybe our products start to look different down the road. These are things that we're looking into and how the program can change. We love the thoughts, we love the ideas, we love the questions, because these are things that, that our team is thinking about as technology changes, as modeling improves, and our program can be adjusted. Believe you me, I mean, I remember going back and trying to look through the profiles and trying to interpret that type of information, and that may not necessarily be the best way moving forward, but we've got to test some of these ideas. We need to explore what works. We also need to be mindful that how does this information get used in a regulatory perspective for floodplain management as well? Can you look at it in a static form in the FIS now, or is it something that we display digitally? So some things that we can explore. I'll ask Laura and Brian if they've got other thoughts about this topic and some of the other questions that are popping up as it relates to different products as well.
Yeah, the only thing that I would add to that, Rick, is, as part of the standard update, we are looking at not just profiles for the 2D, but the flood insurance study inserts that Brian went through, talking about possible more in detail gridded information that would be a pullout in the flood insurance study text, or a more zoomed in area for base flood elevation lines, again, to give people other ways to visualize the information and potentially determine it. To Rick's point, there's still a lot for us to investigate and a lot of different things that we could potentially add to that, those possibilities. But those are some things that we're starting with now in the short term as we continue to look to the long term.
Thank you. Second question, you might have already answered it, but It's from Jamie. Why is the focus on carrying forward the existing products from the 1D world when we could be looking at better products for the future of 2D modeling? We can have more than one set of products depending on the situation.
Yeah, and Jamie, you're absolutely right. I mean, our former FEMA administrator used to always tell us, you know, free the data. You know, there's a lot of information that we have. There's a lot of products that I think are possible as we start to look into this moving forward. How do we serve this information up? How do we present this information to, I know states and local CTPs have their own websites that they're starting to unlock this information and show this data in a different format. So again, we are exploring in those avenues. We're not necessarily limiting ourselves in the thoughts and ideas of where it could go, but it's those things and this type of momentum can help us kind of stir up and explore different concepts that we should try to apply. We don't want to be too limited in what we're doing as we start to look at potential products in the future.
Thank you, Rick. Annie is asking regarding, Annie Young is asking regarding floodways, is there any thought to codifying a no adverse impact policy in the CFR so that if someone encroaches in the floodplain, they need to demonstrate no impact to flood elevations at all?
Yeah, that's a great question, Andy. And I know we've been asked that not only on the mapping side of the fence, but also with the floodplain management side of the fence. Current regulations start to look at, well, you know, hey, this floodway is a floodplain management tool, and we need to consider what impacts that they're going to be to as you start to encroach on that floodplain fringe, and what that cumulative impact is. I don't think, I'll admittedly state that I don't think we've done a great job in modeling or collecting what the cumulative impact would be. So as we start to think about is this possible, I think it's going to require a lot more discussion from the floodplain management community and how we impact rulemaking and regulations change. So it is something that has been brought up in discussions. Laura O'Brien, is there anything else in this space that you guys want to touch on?
Well, Rick, I just mentioned that the regulations we've talked about are the minimum requirements. So that 60.3 floodplain management are the minimum requirements. Communities can choose to adopt higher standards, such as no adverse impact today. So that we're not stopping them from doing that. It's just from a national level, what's the bar that we set from as the minimum, new minimum compared to today.
Thank you. We have some comments, and Mark Pearson just said the fall 2020 standards and guidance maintenance informational summary was just distributed by email today. It provides the summary of changes and proposed updates being discussed by Brian and Laura. Thank you very much, Mark. Is there anything you guys want to add to it?
Yeah, thanks for the comment, Mark. And as you saw in the presentation, there is a timeline as we look at public comment as well as questions for guidance or standards that we're proposing. So we're in that time frame in our guidance and standards update cycle. So you'll see information come out from FEMA through Laura Algio, our engineering mapping COP, and as well as notifications from FEMA.gov about these updates. And
yeah.
Go ahead, Laura. Sorry,
no, yeah, I was just going to add the July community practice is going to talk about the standards changes and provide information on the comment period for that. And then as we go into the August community practice, it'll talk about the guidance changes and some of the language there and talk about the open comment period for that as well. So definitely be on the lookout. Unfortunately, the July one is July 2nd, which is the day before the holiday, but I'm sure everyone will be there at 4 o'clock in the afternoon.
I saw that email coming at 5:39, so it's good that they were able to save it for our presentation and release it for us. So thanks for that.
We have some questions regarding equitable distribution. There's a comment that says equitable distribution sounds subjective. And Jeff's asking, what's equitable distribution? Is the rise the same at all cross sections? Is that what it means? And we also have Andy Bonner responding by saying equitable consideration is in 1D world would still be equal conveyance. Do you guys want to talk about what's meant by that?
Yeah, definitely refer back to the resource tab that CMAC referenced, so you can see the actual language that is being proposed. Andy Bonner's correct. I mean, the discussion of the equitable distributions is very similar to the equal conveyance concept. In essence, again, going back to floodway being a floodplain management tool, how are we looking at both sides of the floodplain so that the floodway isn't getting overtly pushed to one side? What does that start to look like as far as impacts on both sides of the overbanks? That's where we're trying to get to as far as using that language.
Thank you, Rick. Alan Taylor is asking, what about replacing a rise floodway analysis with depth velocity relationships to physically identify high hazards and primary flow path? 2D modeling can be applied directly. I have a hard time understanding the question. What about replacing a rise floodway analysis with depth/velocity relationships to physically identify high hazards and primary flow paths? 2D modeling can be applied directly to these DV determinations, but not floodway. So I think the question is, can the no-rise analysis be replaced by a DV analysis?
Yeah, that's a great question, and I'll defer to Laura and Brian. We've been coordinating with the Army Corps of Engineers, the HEC, and some of the testing and work that we're doing there. So I'll let Laura and Brian take this one.
Yeah, and some of it goes back to, you know, what Rick was saying about it being a floodplain management tool, right? It's the depth time velocity gives us a lot of good information about risk and hazard, and those are really good pieces of information to share with communities, have an understanding of where their risks are and where those high hazard areas are. But as far as the floodplain management requirements being tied to that depth, those are, I mean, being tied to the height of 1 foot of a rise. Those are codified in regulation currently. We are looking at how using different inputs to the modeling and different methodologies in the modeling might impact what that rise might be and how to extrapolate it. In the presentation, we talked a little bit about long-term goals too, which is, do we need to look at something different, such as a depth times velocity or something like that? But we have to keep in mind that floodway is a kind of a construct, right, of assuming that there's development there, not an actual what's on the ground case. And so those are sort of the things that we're balancing, both looking at the hazard information as well as balancing that need for that a future case of where there might be development there and what the impacts of that development would be in that fringe area.
Thank you, Laura.
Yeah, I'd just say for now, yeah, we're still looking at being tied to surcharge as well. So there's other factors can certainly come into play, but surcharge is at least the minimum factor that we're going to be looking at for floodway delineation.
And one thing to consider is that down the road, there's nothing really stopping us from showing this type of information. We have our flood risk products, our non-regulatory products. We know that you know, people have been referencing the depth versus velocity reports that I know have been conducted in Australia. I know there was a report done in Colorado. These are all great indicators, as Laura said, of risks. So there's the possibility to start to reflect this type of information through different means more than what we currently show on the firm.
Yeah, and one of the non-regulatory products that's being added was one of the last standards that we talked about is the floodway elevation. But that's not like your water surface elevation, but where your floodway rises are, to kind of give an idea of where those higher risk areas are within the boundaries of the floodway too. So there's some different products that we're looking at delivering as far as those non-regulatory to help inform communities as well through this process.
Thank you. Jason is asking, have there been any pilot studies or comparisons of the DV approach versus the unit discharge averaging approach that are pointing FEMA in the direction of either?
Yeah, I think back to the exploration that we're doing. We've even had some conversations with Harris County, Texas, something that they've been proposing with FEMA Region 6. So learning a lot there, learning a lot of the testing that they've been doing. It adds to the conversation. Going back to how can we present this information, this way construct in the future? Is this something that can influence how we represent our regulations and potentially into rulemaking? They're all there. We have had some of these discussions, and it is influencing where we're going. So we still need to do a little bit more testing in this space, but we're seeing a lot of value in discussion of incorporating something, maybe not necessarily full-blown depth and velocity, but again, as we start to explore different alternatives, it's an alternative that I know is out there.
Thank you, Rick. Bill Brown is asking, you reference cumulative impacts, but that would be a future condition. FEMA does not address future conditions in any other hydrologic or hydraulic aspect. Why so with the floodway?
Mr. Brown, great question. So we actually do have future conditions elements that are outside the floodway. There are communities that have adopted future condition hydrology, but your question was mainly on the floodway. People are adding to the conversation that maybe we can use the surcharge as a proxy for future conditions. So if it expands, is this something that we could potentially apply? Again, it's part of the conversation, not necessarily one place where we're leaning one way or the other, but I think it adds value of what we can potentially explore. But again, great question, Bill.
Thank you, Rick. Will these short-term results be incorporated into risk rating 2.0 guidance? How does the 2D floodway alter the current perception of risk?
So the 2D floodway elements or 2D modeling elements are a separate issue, not necessarily related to what's happening in the risk rating 2.0 space. I'm not a risk rating expert by any means, but I know those are two things that aren't necessarily related. CMAC, what was the second part of that question?
Will this change the current perception of risk?
Yeah, I think it's something that again adds to what we can bring to the table. You may have seen other presentations talk about our movement from the binary in or out to graduated hazard, graduated risk elements. So having the information in 2D modeling is something that can definitely expand our view in a graduated hazard. And then as we apply that to a location or a structure to graduated risk. So I think all of these things definitely add to that pivot we're trying to make between our current program and what the future of flood risk data could offer down the road.
So we're running out of time. Our last question for you guys is to get a BFE on current maps. We look at the profile of a river or creek. How do we determine the BFE from the new maps based off of 2D models?
I will defer to Brian on this one and Laura as we talk about BFE placement. I know that was also in the presentation in some detail.
Yeah, it's still to be finalized in implementation, but you saw on one of the slides there's an insert capability showing the grid with elevation locations at certain nodes of that grid and along with BFE lines. And then also profile baselines could be used. So nothing's off the table. It's just looking to supplement maybe a suite of things for the user depending on the characteristics of the flooding source.
With that, thank you very much. This was a great presentation. And I'd like to thank our sponsor again, Stantec, for sponsoring this portion of the day. Thank you very much, and this concludes our session.